This is a sulfur cube. Very cute, very bouncy, but not very smart. Or is it? You see, there exists a phenomenon called emergence, where the whole is more than the sum of its parts. A computer, for example, is made of transistors that individually can only allow or block current flow. Clump enough transistors together and suddenly they can do math, run programs, and play the very video you're watching right now. If we go one step above transistors we get logic gates, and with logic gates we can build any logic circuit we want. There are, however, multiple types of logic gates that have different functions, and it is important that we quickly gloss over some of them. Right here we have a traditional NOT gate. This is the simplest logic gate. If we input a 1 it outputs a 0, and if we input a 0 it outputs a 1. The output is always the opposite of the input. To describe the behavior of each logic gate, there exists a so-called truth table. This is the truth table for a NOT gate, and as you can see, it precisely describes what it does. Now, how does a NOT gate made with sulfur cubes look like? It turns out, all that's needed is 2 pistons and a pressure plate. When the input is off, the sulfur cube rests on the pressure plate, outputting a 1. If however we turn the input on by flipping this lever, the sulfur cube gets sent upward, off the pressure plate, and is kept in place by the second piston, outputting a 0. By flipping the lever again, inputting a 0, the sulfur cube falls back down on the pressure plate, outputting a 1. This is exactly what we want. Let's now look at an OR gate, and I promise this is very relevant. This gate has 2 inputs and 1 output. If either input is a 1, the output is a 1. The output is also a 1 if both inputs are 1, which was confusing for me at first, but it makes sense once you think of the OR gate as turning on when at least one input is on. Let's now connect a NOT gate on each input of the OR gate, like this. This is now no longer an OR gate, but a NAND gate. A NAND gate outputs a 1 unless both inputs are 0. It's the opposite of an AND gate, which outputs a 1 only if both inputs are 1. If we replace the traditional torch-based NOT gates with the previous sulfur cube NOT gate, we get a sulfur cube NAND gate. You could say I'm cheating by not making a dedicated sulfur cube OR gate, but given it's so simple, just a redstone wire, I think it's an acceptable compromise. But in any case, why did I just go through all this effort making an AND gate? Well, as it turns out, NAND gates are so-called functionally complete, meaning that any logic gate can be built out of NAND gates. In turn, any logic circuit can be built using NAND gates, meaning right now we have everything we need in order to make a circuit that adds 2 numbers together. In fact, I've already built that circuit, and it's right behind me. First, however, let's look at binary numbers again. The logic gates can only speak binary as we already saw, so every number we want to input must be converted into binary. Let's say we have a 4-bit binary number, 0110, that we want to convert into decimal. To do this, imagine a number below each bit, starting with 1 underneath the rightmost bit, going to 2, 4, 8 and so on and so forth, multiplying the previous number by 2 as we go to the left. Now, take each number and multiply it by the bit above it. In this case, we'll have 1 times 0 equals 0, 2 times 1 equals 2, 4 times 1 equals 4, and 8 times 0 equals 0. Now, we add all the results together, so that's 0 plus 2 plus 4 plus 0 is equal to 6. In the end, 0110 is equal to 6. Back to the sulfur cubes, let's do a test addition, 2 plus 3. 2 is 2 plus 0 meaning 1 0 in binary, and 3 is 2 plus 1 meaning 1 1 in binary. Inputting this into the machine, slowly, otherwise the sulfur cubes can get stuck in the logic gate breaking the circuit, we get 1 0 1 as the output. Decoding that, we have 1 times 1 plus 2 times 0 plus 4 times 1, which is in fact 5. With this, we have proven that sulfur cubes can in fact do math. Getting anywhere past this point is impossible though, I mean, it's not like we'll ever see a sulfur cube computer or something. But what if it was possible? There's one more circuit I've been working on, this sulfur cube SR latch. With this, it's possible to build sulfur cube computer memory, which is another piece of the puzzle potentially getting us closer to a working sulfur cube computer. The biggest problem right now is speed and size. Sulfur cubes can often get stuck on the pressure plate if the input switch is too fast. This not only damages the cube, it's also really annoying to troubleshoot and fix. Right now, sulfur cube gate technology is equivalent to old vacuum tubes. Before the invention of the transistor there was the vacuum tube, which was used to build computers and logic circuits. They were slow, large, and used a lot of power. Through more research, however, it may be possible to build a fast, tiny sulfur cube logic gate to make a computer out of. It won't be better than using torches, but it would surely be funny. And with that, thanks for watching.